Okay, so the integrated law is basically rate law is basically just using the rate law normally, but it's based upon, how many of you guys have taken calculus?
Calculus 1?
Just me.
Me?
Just you? So, two of you guys. Okay. So when we talk about rate is going to be equal to K, K being that constant. And if it's a zero order, it's going to be A to the 0 power. So we're not going to have anything, right? But if we look at rate, what rate basically means is the change in temperature. I mean, not change in temperature, change in concentration. Over the change in time, right? And when you're trying to make a function of this, when you want the rate constant as a function of time, we can sit there and do something called the derivative, right? So d concentration, the change in concentration, over d the function of time. Since most of you guys have not taken calculus yet, or not, only a few of you guys have, I'm just going to kind of talk you guys through this, and you're not going to need to know how the equations were truly derived, but I'm just going to kind of give you an idea. So there is a mathematical process where we can sit there and relate the time and try to figure out, the time as a function of concentration. So since we know that this is the equation in a 0 order reaction, basically meaning that this guy's 0. So we can split this up to d, the change in A of concentration A is going to be equal to K A naught dt. And we'll take this guy as an integral from A naught to AT. And this guy is going to be from 0 to T. And when we do this, we're going to end up with what we call, like I said, the case of a 0 order reaction. So bottom line is, we know that rate is going to be a function. The concentration is going to be a function of time. So that change in concentration is going to be a function of time. That's going to be the take-home message, right? And so after you do the integration of this, you're going to end up with essentially this one. So okay, so this represents a 0 order integrated rate law. And so again, time is going to be changing. As time changes, this concentration is going to change. This is going to be your initial concentration at time 0. And then this guy is going to be our rate constant. Now, if you plot this guy is going to be linear. And you're going to try to set up all of your different integrated rate laws so that they're going to be linear. So you'll be able to, so it'll be easier to understand, easier to see. And I'll show you that here in a second. Okay, so here, this is just basically showing you linear. This is a 0 order decomposition reaction. And so as you can see, the line is nicely in linear, where this is a 1st order decomposition reaction. And then in this case, you can kind of see that the line is kind of sloping. And so that line sloping is a 1st order reaction. And that's going to be a logarithmic type of slope. So again, this is just showing you how the derivative is found. And at the end of the day, so for a first order reaction, you're going to end up with this guy. Okay, so you have Ln, the concentration of A at time t, and then this is going to be your initial concentration, and still your rate constant, and then t is going to be. Okay, so now we often will use these integrated rate laws to sit there and determine time that a reaction is going to take, right? Rather than when we had the other experiments where we had all of the data. So if you've done the experiment, you have your rate constant already, you know where you're going to start off with, right? So then you can sit there and calculate it based upon time, how much concentration you're going to either make or you're going to lose during that time period. Okay, so this is often used when we're trying to determine, let's say, the half-life of something like radioactivity, or the half-life of proteins being turned over for a biological function, or the half-life of a drug in a human's body.
Yeah, I remember having to do that in calculus.
Yeah, yeah. So it's all coming back now, isn't it? Yeah. Okay, so in the case of your half-life, you're going to end up with just this equation. So if we go back to the equation earlier where we have the Ln first order reaction, where we have Ln A T over A naught is equal to minus KT. So for the half-life of something, you're saying that you're going to end up with half the concentration of what you started out initially, right? So then you're basically saying that your Ln is going to be 1/2. Okay, so you have half the concentration than what you initially started out. Oops, sorry, not Ln is equal to 1/2. Ln 1/2 is equal to minus KT. So if we want to solve for T, that would be T 1/2. So then you get Ln minus Ln T 1/2 over K is going to equal T 1/2. And so this guy is just going to equal this equation right here. Okay, so anytime that you're calculating the half-life of something, and you know that it's a first order reaction, then you can always use this value here. Are you with me so far?
Yeah.
Okay.
Yes.
So now let's talk about how you would go about using the first order reaction, or the first order integrated rate law. Okay, cyclopropane undergoes decomposition by a first order kinetics with a rate constant of 9.20 times 10 to the minus 3 seconds at 500 degrees Celsius. How many minutes will it take for 80.0% of the original cyclopropane to decompose? Okay, So in this case, we're getting down and we're losing 80% of the original cycle propane. So then my concentration at time t is going to be how much? How much am I going to have left?
20%.
20%. So initially, I started out with 100%. So then I'll put L in 20 over 100. And then we have, this is our value for K. It's our rate constant. So K is going to be 9.20 times 10 to the minus 3. And that's going to be seconds. And T. So we're solving for T. So we get T is going to equal.
Wait, would it be positive 9.2? Or would it be negative?
Negative. I forgot my negative. There we go. Because it's negative K. So then it'll be ln So ln 0.2 times or divided by 9.2 times 10 to the negative 3. That all should be negative. And we plug and chug that. Okay. Let's see. What do you guys get?
I got 174.9.
Okay. And that'll be seconds. So 175 seconds. And if we change that to minutes, because we want it in minutes. So how many minutes are in a second?
60. Or 60 seconds in a minute.
60 seconds in a minute. Okay. Oops.
And I got 2.9.
Okay, 2.91. Piece of cake?
Yes.
Yeah.
Okay. So the biggest thing that people do here is that they first want to use that 80% because that's what they see. They don't think about the fact that you lost 80% from what you originally started on. Okay. So be sure that you make sure you understand that part. Okay. Okay, so here is a half-life example. How many minutes will it take for a reactant concentration to drop from 0.150 molar to 0.0300 molar for a first order kinetics reaction? So the half-life is 8.50 minutes.
So for this one, you're trying to find the constant, K?
That's right. So then we can use that equation where we have T 1/2 equals 0.693 divided by K. Solve for K. Okay, what did you guys end up for K? Is that what you end up with?
Yeah, that's pretty much what I got.
Okay, good. Okay, so then we have K. So how can we use that?
Wait, what was the question?
I said, so now what are we going to use that K for? So they want to know how many minutes will it take for the reactant concentration to drop from 0.150 molar to 0.0300 molar.
Oh yeah, you have to find T now, or time in minutes.
Okay, so my equation is going to be minus KT equals ln concentration of A at T divided by the initial concentration, A naught. So we'll get T is going to equal ln sorry. Trying to conserve room there. Can you guys see my little chicken scratch there?
Yeah.
We plug in those values. That's 0.150 over oops, 0.0300 molar over 0.150 molar. Natural log divided by 0.0815 over a second or minutes. So we plug inside that. What do you guys get?
And I got 19.7.
Okay, piece of cake.
Yeah.
Yes.
Good, I love hearing that. Okay, so a second order integrated rate law is, so if we're starting with this as our second order rate law, and we know that rate is going to be that difference over concentration over T. So when you do the integrated version of that, you're going to end up with this equation, okay? And so right now we have the second order rate law, we have the first order, first order integrated rate law. I'm going to use this side. That's the integral, which was natural log concentration of AT over A naught. It's going to equal minus KT. And then we have the zero order integral rate law. So, and that one's going to be AT minus concentration of A naught equals minus KT. Okay, so these are going to be kind of your three options to kind of use. And so you want to make sure that you're paying attention to the order of the integral rate law, or you want to be able to sit there and solve it. Okay, so here it says, use the correct integrated rate law to calculate the time in seconds for the initial concentration of 1.5 molar to decrease to 1.00 molar using the following rate law. Okay, so what type of integrated rate law will we have?
The second order?
It's a second order because it's guys to the second power. So then we know that we're going to be using 1 over concentration of AT minus 1 over the concentration of A naught equals negative KT. Okay. What else are we given from this equation here? What is this here?
Isn't that K?
That's K. So we know that this equals K. So now we have everything that we need to calculate the time. Just need to change our equation around. Yeah, this is your wheelhouse, it seems.
We literally just went over this in calculus like a couple weeks ago. The equations were a little different, but it's like basically the same thing.
Really? That's cool.
Yeah.
So that's going to equal T. Oops. Okay, so we plug and chug. And what do you guys end up with?
I got 1.6 1.67.
Okay, so it will be 1.67 seconds. Piece of cake?
Yeah.
Okay. So now I'm going to show you how to do this next one graphically. It says calculate the rate constant using the graphical method for the first order decomposition of ammonia into its element given the following data. So I have T at time equals 0. We're starting off with 4.000 concentration or molar of ammonia. At T equals 1, 0, 0, we have 3.986. When T equals 2, we have 3.974. Okay, so what we're going to do here is, we know that it's a first order decomposition reaction. So what is going to be the integrated rate law for a first order decomposition reaction?
Wait, what was the question again?
So what is going to be the equation for a first order decomposition reaction?
Oh,
first order reaction.
Natural log of A of T over A of naught equals negative K of T.
Okay, so we're going to kind of change this guy around so that we can make it into something that we know. So what is the generic equation for a line? Do you guys remember?
For linear?
A linear, yeah.
Y equals mx plus b.
Okay, so we get y equals mx plus b. So what we're going to do, we're going to modify this equation so that it looks like that. So if we remember our rules about logarithmics, we can sit there and do this. Since this is a division that's going on internally here, so that's the same thing as saying ln a to the t minus ln a naught. And that equals negative kt. So we know that the ln a naught is going to be a constant. So if we bring this over, ln t equals minus kt plus ln a naught. Okay. Okay, so we know that this equation is a function of time. So our ln a t is going to serve as our y. This is going to serve as our mx. And then this is going to serve as our b. Can you see it? Yes, no, maybe?
Yeah.
Okay, so basically we have a line. So we can sit there and plug this guy into Excel or Google Docs or whatever, and then try to find the slope of that line. So let me show you how to do that. So everybody got this down so I can move on to the next part?
Yeah.
Oh, did you guys want a copy of these slides anyway? I'll put them in the chat.
Can you do that?
I can. Okay, do you guys see it in the chat?
Yeah, I was gonna download it.
Were you able to download it? Okay.
Yeah, it's downloading.
Okay, so I'm going to enter my data in the table. So this is my time. Seconds. This is my concentration. And so since we're working with the log, we want to take the log of that concentration. So to do that, we're going to enter ln, comma, then we're going to select our concentration, hit return, and then we're able to drag it all the way down. Okay, so then now we have this guy in terms of the log, which kind of acts like my y. So we're going to make this guy my y value, and then my t value is going to be my x value. So I'm going to select this, control, I'm going to select this. Then I'm going to go to insert, and I'm going to choose my graph. So I'm going to use a scatter plot. Come on. Okay. So I'm going to select this part. Got to go to trend line, hit trend line. And actually, I'm going to go so I can hit more options. Maybe. If it lets me. Then I'm going to hit the one that says more options. So then if you go over here to the Excel, you hit the graph. It'll actually show you your different options. Can you guys see that?
Yeah.
Okay, so you want to go to display equation on chart, and you want to display your R squared value. Your R squared value, the closer it is to 1, the better it is for fitting that curve, okay? And so if you take a look at this one, this guy is pretty good. It's your R squared is going to equal 0.9981. So we have a pretty good R squared value right now, okay? But if you take a look at this equation, we have it in this format. So my y is going to be my ln. So my x is going to equal that time. And then, so this guy here is going to represent my k, right? So I have my minus already there. So my k is going to be equal to is going to be equal to 0.0033. And the units are going to be 1/seconds. Okay, because we know that the log of this guy would be considered unitless because these guys are going to cancel each other out. Okay, so I believe that answers my question. Calculate the rate constant. Simple?
Yeah.
Anyone having trouble with that? Okay, anybody who doesn't answer want to give me $1 million?
Are they going to be on the test?
Yes, on your next test. Oh, not this test. It's not going to be on this test. This test.
Oh, okay.
Okay?
Yeah.
Good, good.
And we're gonna have one more test before the final, or just the final after this?
I think you guys are just gonna have a final because you guys have done, this will be your second test. I'm gonna give you one more so you don't have as much stuff on the
Oh, okay.
Okay. So you guys good so far?
Yes.
Yeah.
And I like giving you guys Excel questions. Don't I, Jessica?
Yes, yes, you do.
Yes. Okay, so this is just basically showing you the data plotted in another program.
So if
Okay.
you give a graph or kind of like with the other slide, if you give them a question like that, and like what order is it? We take a look at our slope, right? Because our K constant is essentially your slope, right?
That is a good question. So I'm glad you asked that question, because this question will answer that question.
Okay.
Okay. It says, here's the question. Determine the order of the equation from the following data. Okay. So here's the time. Here's the concentrations at the different times. Okay. So we know that a zero order reaction integral rate law uses the following equation. A, concentration of AT minus A naught equals negative KT. Okay, now if we look at this one, this guy's already kind of set up to be linear. This is your Y, this is your X. We just need to change the equation around so that we have the A naught over here. So it's just a linear equation. Okay. The logarithmic equation, we've already shown how to make that linear. So I'm just going to write it in its nice form for the first order reaction. So we get ln AT equals minus KT plus ln A naught. Okay, and we know that this guy is going to be linear in this case, where this is going to act like your Y and this is going to act like your X. And then in the case of a second order reaction, we know that we're going to have 1 over A T is going to equal minus KT plus 1 over A naught. Fix this, or does it look like a knot? Okay, so this here is going to serve as my Y. And then, of course, this is going to be the X, or the XM, or MX. And then this is going to be my B. Okay. So what we're going to do is we're going to take all the data and then we're going to change it to the different forms. And we're going to see which curve fits the best. Okay. So the first case, the A0, is going to be exactly the way that we set it up as it is in the table, right? So then we're just going to use that data straight. Now the logarithmic, or the natural log of AT, all that is all we're going to do is go equal ln parentheses, click the original concentration, hit return. And then we're going to do that for all of the other ones below it. So we're just going to drag it down. And then for the second order reaction, we're just going to go 1 over the concentration. So 1 over 1. So again, we're going to put equal 1 divided by the concentration. And then we're just going to drag that down. Okay. So, chart. Okay, so then I want to graph all of these. So what I'm going to do is select all of them. I'm going to go to insert, hit scatter. This is my scatter plot. So I'm going to hit plus, go down to the trends, and then I'm going to have to do each one independently. Oops. Actually, come on now. More options. We hit the graph. I want to display the equation, and I want to display the R. Okay, so this is the equation for the blue line. So then that's my, the blue line represents the zero order reaction. So then I'm gonna go ahead and repeat again. More options. And then this time I'm gonna do for the natural log, the concentration T. I'm gonna go ahead and hit OK, hit the graph. We're gonna put the display equation on the chart and display the R squared value. So now this is the orange line down here. Okay, and then I'm gonna do the last one. So more options. 1 over the concentration. Okay. Okay, so here are all 3 of the reactions. Now, can you tell me, looking at the R, which one is going to be the one that fits the line the best? The gray, the blue, or the orange? Boy, I can hear crickets. Anybody there? Did I lose everyone?
I don't know, the gray maybe, because it's R squared equals 1.
Yes. So because remember, I told you, I said, if your R squared is you're trying to get your R squared as close to 1 as you could possibly get. That means that the graph fits the data very well. So here my R squared is exactly 1. Here my R squared is 0.94. Here my R squared is 0.863. So then this tells me that this guy fits the data perfectly, right? So then I would say that my kinetics, the order for the kinetics for this reaction is a second order reaction, because the gray represents 1 over the concentration, which is our second order. Do you guys see how to use that?
Yeah, it's just like the closest 1 to 1 though, right? It's not usually exactly 1, right?
No, it is the one that's closest to 1, yes.
Okay.
It's rare that you get perfect data. And if you do, you're a god. Okay? Questions, concerns, Cash? Okay, good. So does that answer your question, Jessica?
Yes. So Excel, right?
Excel. Yeah.
Like Excel.
Yes, and this will work in Google Docs and also Apple Pages, and the techniques that I teach you in Excel, they also work in Google Docs, dragging those corners and all that stuff. It all works the same.
Okay.
Okay. Okay, good. Okay. So this is just showing you another way that you can graph the data, and you can actually see the curve a little bit cleaner when you graph them independently. But I like doing them together so I can see the different R values. It saves me so much more time. Got it all on one slide, you know, it's easy. So this is that first order reaction. Again, you can kind of see that it has that angle slope, so it's not a nice fit. Not the nicest fit. And then here, this is that second order reaction. Okay. Questions, concerns, Cash? Excellent. Okay, so let's move on. So the collision theory. So in the case of kinetics, we know that the concentration is gonna affect kinetics. The more stuff you have, the more you're able to sit there and produce, right? The faster that reaction is gonna happen. So let's take this for instance. If I had two gases being pumped into a room, one is being pumped in on one side, one is being pumped in on the other side. I only put in a little bit of each gas, right? And they're in this big ass room. What is the probability of those gas molecules finding each other and reacting or colliding with each other?
Small.
Very small, okay? Now, if I decide to fill the whole room with a whole bunch of the gas, and there's a lot more, what is the probability of those two different molecules coming together and reacting with each other?
Very likely.
It's very likely, right? So it's going to increase. So that proximity and that concentration is going to play a huge part. Make sense?
Yeah.
Yes.
Okay. So now let's say I get the room and I put the room at really cold temperature. Is that going to cause my reaction to happen faster or slower?
Slower.
Lower.
Okay. I like the glow sticks, right?
Yeah.
Yes.
So the other thing is the state. If I have a big old brick of one chemical and then the other chemical is a gas, am I going to be able to get to the molecules that are in the center of that, the chemical that's a big ass brick?
No.
No.
No. So then I'm limited by just the surface area. Right?
Yes.
And then the last thing is the catalyst. Catalyst affects the orientation of the molecule so that you can increase the speed of the reaction. So you kind of get it in right orientation so that it can be attacked the way you want it to be attacked. You break the bonds that you want to break, you reform the bonds that you want to reform. Okay? Okay, so let's talk about activation energy. So the activation energy is the minimal energy that is required to get the energy to get a chemical reaction started. So I kind of like thinking of the activation energy, kind of like the energy to get over that hump, right? Say your car runs out of gas, you're on a mountain, right? So you're thinking to yourself, I ran out of gas, I'm on this damn mountain. I have two options, right? I can push my car up over that top of the hill, and then I could just coast down because I know that there's probably a gas station down on the other side, or I could just sit here, right? More than likely, you're going to be pushing your car over that hill and hoping that you get to that top of the mountain, slope down. Okay? So the energy to get over that hill is considered your activation. Okay? And then when you get over to the top, you're able to sit there and coast down. And then it takes less energy, less potential energy for you to sit there and do anything. Make sense? So kind of like this. Okay? So this is A plus B. We have to get over this hill for this reaction to occur to make C plus D. Are you with me?
Kind of.
Good. Okay, so this is called the Arrhenius equation, and it basically relates temperature to the activation energy, also to the constant. So the constant is dependent on temperature. So your rate constant is dependent on temperature. So the rate constant that you have at a certain temperature is going to be different at the rate constant for something at a higher temperature. right? And then this is the equation that we would actually use to sit there and calculate. Okay, so let's talk about some of the players in this equation. So of course, you know that this guy represents your rate constant, or the K, I should say, represents your rate constant. This here is your activation energy. This here is just the gas law written in different units. So it's 8.314 joules per Kelvin moles. It's really the same units as the 0.0821. Only thing, this guy is written in ATM liters per moles Kelvin. So the ATM liters, if we did the conversion, we can convert that to joules, and we'd end up with exactly the 8.314. So T is temperature. I could spell. Okay, and then the A represents a constant. Okay, are you good?
Yeah.
Okay, so one way that we could sit there and do this is if we have this equation here, or one way that we can use this equation, we have K at one temperature, ln K at another temperature is going to equal minus EA. So the activation energy isn't going to be different. The only thing that's going to be changing is temperature. The activation energy is going to be the same under both circumstances of the reaction. Times 1 over T. We know that T is going to be changing. So we're going to call this T1 plus ln, and we know that ln A is a constant. Okay. And we take this equation over 2 plus ln A and let's just subtract these equations from each other. So we get ln K1 over ln K2 equals minus EA over R times, subtract the whole thing. So that'll be EA times 1 over T1 minus 1 over T2. And then the LNAs are going to cancel each other out. So you're just left with this. So if you have 2 points, you can sit there and use that to sit there and calculate the activation energy for one of the unknowns if you know the activation energy. Okay, make sense?
Yeah. That kind of looks similar to, like, what is it, the Clay?
That's right.
Whatever equation.
Yes, they're very, very, very similar, right? One thing, one was dealing with pressure. This one is dealing with a constant gas, kinetics constant.
Yeah.
Yeah. Okay, so here it says calculate the activation energy for a reaction with a rate constant of 4.5 times 10 to the minus 5 molar seconds at 195 degrees Celsius and 3.20 times 10 to the minus 3 molar seconds at 258 degrees Celsius. Okay, so what do I need to do here?
Like to set it up.
Okay, so let's see, what do we have? This is going to be my K1. This is going to be my T1. I have to change my T into Kelvin. So how do I change my T into Kelvin?
You add 273.
Eight, 468. Okay, so this guy's going to be my K2. And we're going to do the same thing to this guy at 273. $531. Kelvin. Okay, so then I can solve this equation for E. So I'll get E. A is going to equal ln K1 over K2 times negative R divided by 1 over T1 minus 1 over T2 So my R is 8.314 joules per moles Kelvin. Times ln 4.5 times 10 to the negative 5. And that's 1 over molar seconds divided by 3.20 times 10 to the minus 3, 1 over molar seconds, all divided by, 1 over 468 minus 1 over 531. Okay. So if you do the math, I think I ended up with 137. I can't remember the numbers following it. Let me put it in real quick. So now I've got my minus sign there. inverse times 8.4. Let's put that one up. I think it's 726 joules per mole. And then it'll be 740 kilojoules. Oops. Sorry. There we go. Okay, questions, concerns, Cash? No questions? Excellent, great. Okay, so you could also have plugged it in and graphed it. So if you're given multiple points, multiple temperatures, you can sit there and graph it, and then you can sit there and get the slope of that curve. And in this case, you'd be using that E divided by R as your slope. And so you just have to multiply it by R to get your EA. Okay, questions? Are you there?
Yeah.
Okay, so this is just basically showing you that slope. So if you have two, and this, you could have done it with the 2 points as well. You could have graphed it and used it to determine your slope, and then use that to calculate your EA. Okay, last parts. So reaction mechanisms. So there's a couple things that you guys want to know. So when we balance the chemical equation, right, that's not going to affect the rate constant. The reason why it doesn't affect the rate constants, it doesn't affect the rate, the kinetics of the reaction, right? So we're not using the stoichiometric determinants as ways of affecting the rates. And the reason why we don't do that is because a lot of times there's intermediates, byproducts that are made in between that reaction. So we'll make one product, and then we'll make another product, and then we'll make another product. Because we don't know all of the intermediates, right? The only thing that we know is the starting reactants and the end products. Then we can't use the chemical equation to sit there and do the kinetics. If we did know all of those reaction mechanics, then we would be able to sit there and use that balance equation to provide that information. But we would need all of those intermediate reactions. Does that make sense? So in other words, we have a black box. We put this in and we get this out. We don't know all of the steps in the middle.
Oh, yeah.
Okay. And so because we don't know all of the steps in the middles, we can't use that balance equations to sit there and calculate the true rate law. Although you can if you know all the intermediates. Okay. Or true rate of reaction. Okay, so, and the reaction mechanic types, they could be unimolecular, basically meaning that you're going to make one molecule. It could be bimolecular, or it could be teramolecular, right? So basically, you could make one molecule. You could have something that ends up making two different steps to make a molecule, or you could take something that takes even more than that. Okay. So the thing that you want to remember, though, is that if you do have a reaction and you have all the intermediates, so the slowest step is going to be called the rate determining step, because that's going to determine the overall rate of the reaction, the slowest point. So if your other parts are like really, really fast, and then it takes 2 years to sit there and make this last product, then the rate of the reaction is going to be 2 years, right? Because all the other stuff is being made fast, but this part is the last part that goes in. And so you're looking at that product, it's going to take 2 years. Are you with me? Gracia, what did I just say? Gracia, are you awake?
I think she left the meeting, Dr. Henry.
Oh, she left? Okay. Okay, Mauricio, what did I say?
You said at one part of 2 years and the rate reaction is 2 years.
Okay. So it's always going to be the slowest step that's going to be a rate determining step. Okay. Good.
Yes.
Okay, and the last part is catalyst. So catalysis is just basically the process of using a catalyst. So catalyst can be a couple of things. We could have inorganic catalysts, metals. We could have organic catalysts, or hydrocarbons. We could have biological catalysts, enzymes. So anything that basically will speed up a reaction is called a catalyst, and it changes the overall rate. Often how it changes the rate is by optimizing the orientation of the reactants. So you set it up so it's acting on the surface of a piece of metal, so that gives it room to sit there and bind the right components or to attack. And you'll see this more playing a part when we get into organic chemistry, how we utilize catalysts to sit there and get certain chemicals formed. Okay. Ultimately, what happens is that the catalyst is, as I said, optimizing the orientation, but it's lowering the activation. So remember when you guys were pushing the car up the hill to get over the hill in the case of the activation energy? So think of it as you're pushing the car up the hill, and then you find a tunnel that goes through the mountain, right? Or go through the hill. So wouldn't you go through that hill instead of trying to push that car all over that mountain?
Yeah.
Yeah. Okay. So that's basically what a catalyst does. It just changes the height of that activation energy. So it's not as much energy needed to get there. Okay. And catalysts can be classified as homogeneous. Basically, they're going to be like enzymes in a solution. So it's like a homogeneous solution, kind of like that. Or it can be heterogeneous. You have a metal in a solution, you know. Oops. And so this is just an example of how a catalyst reaction that's been catalyzed compared to one that isn't catalyzed, uncatalyzed. Okay, so this is the normal activation energy. This is the case of a catalyzed reaction. So the hill is less, so it's easier to get over that hill. Questions, concerns, cash, credit, Kool-Aid?
Kool-Aid.
Okay, so let's talk about your lab real quick. Okay, so you guys are gonna have 3 eggs, right? That you've put vinegar. You've used vinegar to basically remove the shell. Okay.
Well, it softened it, like it's super soft now.
Yeah, so it should be, yeah. So all you should have is basically the inner part of the egg. So it's just the cell, right? So what you're gonna do is you're gonna put one of your eggs in water. You're gonna put your other egg in, you're going to put it in 15% sugar. You want to make sure your sugar is completely dissolved.
Wait, the sugar in the water?
Yep.
Okay.
And then you're going to put your last egg, you're going to leave it in the vinegar solution that it's in.
The vinegar is like all absorbed at this point. There's none left in the jars.
Okay, so then if you have a fresh vinegar, use the fresh vinegar. So. Okay. Okay, and so then you're going to basically let it sit till next week. Okay. And then next week, what you guys are going to do is calculate the osmotic pressure from the different solutions. So if one of them cracked, so if you kind of touched it, it should be, you should have most of the shell off. And so if you kind of just wash it with water, you'll get the remnants, because all you're going to pretty much have left is like little remnants of shell on the surface. So if you just kind of rinse it a little bit with water, be gentle, because otherwise you can bust it and you don't want to bust it. So the one that's cracked, kind of just leave it in the vinegar, or just keep that in the vinegar, and then use the other two in water and in sugar. Okay. You need to weigh the egg before you put it in those solutions. Weigh before, and then you're going to be weighing it afterwards. Okay. Okay. Now, for your wine or your kombucha, what you guys need to do is you need to go and get fruit. And so it depends on the fruit that you have. I'll have a little table. I'll be putting it up later tonight. So you're going to get about anywhere from 2 pounds to 5 pounds of fruit. If you want your wine to be a little more fruit flavored and things like that, go with a little more fruit. If you want the alcohol and you just want a hint of fruit flavor, then go with the 2 pounds. Okay, and you're going to need a 5 pound bag of sugar, just a small pound of sugar. You know.
That's a lot of sugar.
It's only 5 pounds. It's only this big, you know. Don't worry about the yeast will use it, or the SCOBY will use it. It'll have it'll be very, very flavorful. Okay, questions, concerns? Batch.
For one of the solutions, when it says 15% sugar, does it have to be exactly 15%?
You want it to get as close to 15% as you can. So, and you're going to put these, it's probably best if you have your typical beakers. I think your egg will kind of fit nicely in those. And I think you should have 3. If not, use a 250. And I know that you should have at least one 500. So use that. Yeah.
And you want us to calculate the 15% by weight, right?
Yes.
Of the sugar and water. Okay.
Yep. Well, you know the density of water, so you can use the number of mils in that case, right?
Yeah, I just want to make sure.
Anything else? Okay. Cool. So then I will see you guys on Wednesday.